So thank you for having me here and for opportunity to speak. My talk, and also I could not resist a desire to start giving a talk and just cover this blackboard from that cutoff to that cutoff. I only have 35 minutes. So my talk is about Euclidean operator growth. Euclidean operator growth and quantum chaos. Since I don't have that much time, I would like to start with sort of the message. Then there will be maybe a part where I do some rigorous statistical mechanical calculation. I will sketch the calculation. Maybe toward the end, I will present more physical results. Let me first explain what is the idea. Conventionally, we have a quantum system, let's say something like a quantum spin chain. Think about lattice spin system. You have a local operator. Let's say, always think about one-dimensional spin system, integral or not integrable, doesn't matter. This is your local operator, and we evolve it in the Heisenberg picture. This is, of course, a unitary evolution, and therefore, that was a Hermitian operator. That is still, if A was a Hermitian operator, A of t is a Hermitian operator. Moreover, the norm of A doesn't change. This is a similarity transformation. On all eigenvalues remain the same. The norm of A remains the same. Let's say it was 1. It was always will be 1. So there is no growth in a sense of norm. There is no growth of operators in Minkowski time. But operators spread. And they spread according to such that they obey Lieb-Robinson bound. If we try to calculate A of t and B, without any argument, it means always at time 0. And if they're located distance L apart, and I try to calculate the norm of that, it will be bounded by E minus L minus VT, right? This is a Lieb-Robinson result. So we know that there is an emergent light cone, and operator A spreads. The norm is 1, but this norm spreads in the light cone. It might be localized on the frontier, or it might be spread in here. It doesn't really matter. But it means that if I have an operator sitting here, those two guys commute until the light cone reaches this point. This is the conventional Lieb-Robinson picture. Lieb-Robinson is a bound. But in fact, if you do numerics, if you do further studies, you see that even in non-relativistic systems, operators truly spread like that. Of course, there is they leak out of the light cone. There is a little bit of signal, which is exponentially small out of the light cone. But you can speak of this front wave, which is spreading ballistically. That's basically the gist of operators spreading in Minkowski space. That's a conventional picture. What happens in the Euclidean space? In the Euclidean space, you introduce Euclidean time, let's say simply imaginary time. So now your operator is this one. One thing you can say is that if A was Hermitian, this is a non-Hermitian operator anymore. So that's already something unconventional. But also the norm of this guy doesn't remain to be constant. In fact, it grows, right? You have an enormously, let's say H has positive energies. You choose the vacuum energy to be 0. You have enormously large exponent. Well, here perhaps you have enormously small exponent, but you will also have ground state, and ground state, exponent on the ground state, it's exponent of 0. This is 1. So you will have something which might grow. And in fact, this norm will grow very, very fast. Okay, so I want to study how this norm grows. And why I want to do that? Because there are several reasons to do that. First of all, I want to study this object where A and B are separated by distance L. And let me right away give you the result for this. It turns out that this norm, I will derive a rigorous bound, but it turns out that this norm behaves very, very differently in 1 dimensions and in higher dimensions. In one dimensions, it turns out that this function, it grows very, very fast. It grows double exponentially. I don't know how to, that's a very schematic formula. It grows double exponentially, but it never diverges. Grows very fast, but it never diverges. This is all in the thermodynamic limit, infinite size. But if you consider two-dimensional system or higher dimensional system, you have something like 1 minus E beta, E minus beta star. Well, this is again schematic formula. I'll write a more accurate formula in a minute. And it turns out that in the higher dimensions, there is a critical imaginary time. And you can think of it as something like imaginary time. This is related to related to temperature, at least morally, because technically it's not the same. But at least morally, you say there is critical temperature in higher dimensions. That's because you might have phase transitions. So this is, at first glance, is okay. If you go a little bit deeper, you will see that this B star is not literally related to phase transition. You can have B star even in systems without phase transition. But in fact, I'm saying that in higher dimensions, the growth will explode at some finite imaginary time. Okay? This is a bound. This is a bound. But I will try to argue. I do not know how much time I have. Therefore, I will announce it now as a sort of result. The claim is the following. In the chaotic systems, if the system is chaotic, then this growth is a characteristic. This bound gives you the characteristic growth. Maybe the coefficients needs to be readjusted, but basically in chaotic system in one dimension, the norm will grow double exponentially. And in two dimensions, this growth will explode in finite Euclidean time. Okay? That's a... There's a blow up. There is a singular. You see, if beta is equal to beta star, this is a pole, right? This is a pole. Yeah, that's what I'm saying. My point is the following. If the system is chaotic, this upper bound actually gives you characteristic behavior. I'm not saying that it will literally be saturated. That will be too much to require. But I'm saying if you readjust parameters, maybe introduce some parameter here, that is a behavior in chaotic systems. If you have an integrable system, the behavior will be very, very different. Basically, the growth will be much more tamed, and in particular, in higher dimensions, you will not have a singularity. Right? You will not have a singularity. For example, in the integrable system, you will have something like E beta squared. Okay? So that will be like a Gaussian, not with minus, with plus. It grows very, very fast, but it never explodes. Okay, so that's a difference. That's a qualitative difference. That's why the talk is called Euclidean operator growth is quantum chaos, because I claim as a main physical claim of sort of this work that Euclidean growth can distinguish between chaotic and integrable systems. In the chaotic case, you will have a singularity. In the integrable case, you will not have a singularity. I probably will not have time to go into explanation. There is a qualitative picture which shows that this singularity in the chaotic case can be traced to the fact that the operator becomes ergodic in some orbit of Krylov subspace. If you have an operator and you start acting on this operator by h, you can expand that in the series of nested commutators, and that sort of defines the Krylov subspace, right? So the operator in the time evolution, Euclidean time evolution, the operator can only explore the Krylov subspace. And this singularity, I claim, I argue for, I probably don't have a rigorous proof, but that's the picture which is emerging, is that the singularity is related to the fact that at some finite time, this operator becomes ergodic in this orbit. So it becomes typical in the mathematical sense. It becomes sort of random in this Krylov subspace. In real time, there is no singularity, and in real time, the question of norm doesn't make sense. The norm is always 1. You can speak about ergodicity in the Krylov subspace in Minkowski time. That's an interesting question. I don't really have much to say. For example, I do not know if in chaotic system, if you evolve operator in Minkowski time, if it will be ergodic under this evolution. I do not know. That's a good question to think about. I thought about it. I just don't have an answer. Okay, let's speak a little bit about Lieb-Robinson. There is maybe a chance that my time is running. I do not know if we will have a chance to derive it, but I just want to present you the result. The Lieb-Robinson in Euclidean time, again, it will be different in one dimension and in higher dimensions. In one dimension, morally speaking, it will be exponent beta L divided by L factorial. okay? Exponent beta L divided by L factorial. If this is assuming that L goes to infinity, okay? And this is in 1D. And if I did things correctly, we will see now that it means that in Euclidean time, the operator grows not ballistically, but exponentially. So for this, how would I know that the front wave has approached particular point? That's when this term will become of order 1. And to do this calculation, E beta L is approximately equal L factorial. L factorial is approximately L to the power L, right? So E beta is approximately L, which means that beta, it's a Euclidean time, imaginary time, is logarithm L. Okay, so that's what my sketch, that's my result. And it means that instead of this ballistic propagation, I have a wave which grows exponentially. It's, of course, very different behavior. Now, there are a few, of course, this is a bound. I need to explain additionally that this behavior is saturated. I claim that this behavior, logarithmic spread, is a true spread in chaotic system. I don't really have a rigorous proof. There are a few examples in the literature where people did numerical studies in Euclidean time evolution, and they saw convergence of this process in logarithmic time. I think this is a very intriguing observation, which is indirectly confirming this picture. Okay, so this is in one dimension. In higher dimensions, the situation is the following. You have critical temperature, and therefore you will have a singularity. Well, I will write exactly the same formula. It's a schematic formula, but roughly speaking, you have a singularity. And once you hit the singularity, not only the norm of the operator explodes, actually this commutator explodes as well. Again, this is a bound, but I claim that the picture is the following. The operator in higher dimensions spreads to infinity in finite time. So there is infinite velocity, and the operator just spreads to infinity. Okay? This is a qualitative picture. Again, in integrable models, you can bound the spread even in Euclidean time to be ballistic or to be super ballistic. You can have a bound that beta grows at most at L squared. So in integrable models, you will never have any kind of singularity. So that's a qualitative difference. Okay, any questions at this point? So relativistic, nothing happened. Sorry. If you go to Euclidean space, you still can have more than speed of light propagation. It really doesn't matter. You can consider a system which has relativistic limit. That's fine. Okay. Let me try to derive those bounds. I'll sketch those bounds. So the derivation is sort of very naive. I'll try to bound this quantity. This is a norm of E beta H, AE minus beta H. So this is a sum. I'll just expand it in a sum of nested commutators. Beta to the k factorial, H, H, A. Well, in principle, I need to bound like that. But in a second, I'll just put the modulus inside. I'm making it worse, but I want to do it anyway because that's how I can make the bound. But before I do that, I will remember that my system is local. My system consists of local Hamiltonians of the form HI, where I live on bonds. If you consider one-dimensional spin chain, these are your spins. Operators H live on bonds, right? So something like H1 could be like sigma z plus 1/2. So let's say 1, 2, sigma x1 plus sigma x2. That's an example. That would be like integrable spin chain, right? So it's living on bonds. You can have higher dimensional system. It could be not rectangular lattice. It could be, well, here I'm considering short range, just one bond for simplicity. So these are local guys. If I do local guys, my sum will be as follows. It will be a sum over sets of nested commutators And here I will have, excuse me, I will have k different terms. And let me put modulus here. Okay, this is my bound. Now, if it was a bound in Minkowski space, this would be a stupid way to do it, because I would never be able to recover Lib-Robinson bound this way. Because Lib-Robinson uses the fact that here I have I to the power k. Because of that, I have sign alternation. So to do Lib-Robinson, I need to combine things differently such that those minus signs will cancel each other right away. In Euclidean time evolution, there is no signs. So what I'm doing is not completely stupid. This would be a this bound will be dependent only on modulus of time. Strictly speaking, this bound works along Minkowskian time as well. But along Minkowskian time, this is a completely stupid bound. Well, along Euclidean time, I claim this is a good bound. Okay, so how do I bound that? Well, I say that each HI, modulus of it is smaller than some local coupling constant J. And therefore, I can bound that by sum over k from 0 to infinity, 2j beta to the power k. If I commute h and a, I'm saying that the modulus of that is smaller than 2j modulus of a, right? Because this is ha minus ah, and then I have infinity norm. So this is some sort of, this is an assumption that they commute like Pauli matrices in a constructive way and always add to each other, always add to each other. I do not know any model where that literally happens, such that all of them constructively add to each other, and therefore I bound from above. So I have this term divided by k factorial, and here I have a sum over sets h1, I1, ik multiplied by 1. So this is some combinatorial factor. This is some combinatorial factor. Now, the conventional way to calculate this combinatorial factor, we need to understand what are those i's. Well, in principle, here, that was the full Hamiltonian. So since it was a full Hamiltonian, here I have all terms. But if I include all terms, I will be making a rather stupid mistake. Since I have a nested commutator structure, it's very clear that H has to be living on a bond adjacent to A. Otherwise, it's 0. Once I commuted this guy with A, the next guy has to be living on a bond which is adjacent to this guy, and so on and so forth. So this set of bonds have to grow, literally have to grow one by one, because otherwise the commutator will be 0. This is a crucial point. This will help me to do much better combinatorial. It will help me to do much better accounting of this number. If I don't take this into account, I will result with the following. I will say that there is a norm of H. The norm of H is proportional to the volume. And I will have volume to some power, and that's divergent in the thermodynamic limit. I will do something stupid. It's crucial that I say that the set of bonds is growing. Okay, so here I'm only counting the sequence of those indices such that they're growing. How to do it? The conventional way to do it, rather straightforward way to do it, is the following, is to notice that on many dimensional lattice, I start with some point, and then there are bonds. They are forming some cluster. So I will try to see how many clusters I have, and the number of clusters grows exponentially with the number of bonds. And then for each cluster, in principle, I need to grow them, which means I need to add them one by one in a particular sequence. But we do not know how to calculate that, so people would say, you know, you can bound that as a number of clusters multiplied by the factorial, because you simply ignore that you can add them in a particular order. You say you can add them in any order. So if you do that, let's do it in one dimension. In one dimension, if you have k bonds, so basically there is only k plus 1 clusters. Since A has to be inside, there is only k plus 1 clusters, because you can move those clusters like that. This is a linear term, not very important. So I'm not continuing, I'm doing a sketch. I'm doing a sketch of calculations, or sort of naive calculation. Naive calculation. I'm saying I'm trying to calculate the number of those sets in 1D. So the number of those sets in 1D would be k plus 1. This is a number of clusters. And then the next thing, I need to account for different permutations. So different permutations, people say, let's just multiply by k factorial. I ignore that you can add them one by one in a particular order. So if you do something like that, that's already not good. because this factorial will kill this factorial. And if I continue in a naive way, I will have something like 2j beta k, k factorial multiplied by k factorial, maybe also multiplied by k plus 1. This is less important. This sum is a geometric progression, and therefore it will have singularity at a fixed temperature. Therefore, in one dimension, I will have a singularity, but I promise you there will be no singularity. In fact, it's a known thing. In one dimension, things have to be analytic. So this counting is a bad counting. The counting based on clusters is a bad counting. So what we did in this work, we sort of invented a slightly different counting. Instead of focusing on clusters, we focused on how the clusters grew. So if you give me a set of bonds, a set of operators or a set of bonds in a particular order, assuming that they grew in the right way, so you will adding them one by one. Of course, you can repeat things. If you start here, you can act by this operator, then you can act by this operator, then by this, and then by this. Then you can start acting by these operators again. Okay? So if you have a set like that, go from this set and remove things which appear more than once. So if you started growing in a particular way, that was the first one, that was the second one, that was third, and on the fourth step you acted by this again, just remove it from the set. If you remove it from the set, you will have something like I1, P, and P is smaller than K, and that is a set where things don't repeat itself. And this thing I will call cluster history. So this is more than a geometric picture. This is more than a geometric picture. This is also a history how that cluster grew. Now, let me introduce a function phi of p. This is a number of different cluster histories consisting of p bonds. Okay, so it's a very detailed information. It only knows about how fast cluster grow. It also knows how many ways I can grow each cluster. But let's say I know this function. Let's assume I know this function. If I know this function, then what we did is the following. You can resum this thing exactly and obtain the following formula. I will not do this combinatorics. This is a purely combinatorial problem. You need to do some resumming. It's not completely trivial. Since I only have 12 minutes, I'll skip the derivation and I'll give you the answer. So here I write equality because this is literally going to be equal. Instead of summing over this k, I will be summing over number of bonds in the cluster histories. I will have a number of cluster histories. I will have an auxiliary variable q, I will define in a second, divided by p factorial. Q is an exponent 2 beta j minus 1. So this is an equality. I claim that we did this combinatorics exactly. So the number, so you see, I cannot give you this number in a concise form, but I'm saying that this number multiplied by this exponent divided by factorial summed over k. I'm resumming this temperature, excuse me, I'm resumming this time-dependent piece such that time now is sitting inside q. So this is now some exponent of time. This is a different formula. It's a much smarter formula. Okay? Well, to finish the calculation, I need to know the number of animal histories. How do I know them? Well, in one dimensions, or in fact, for any beta lattices, beta lattice is when you start from a point and you start introducing like branching. You say that you have, I forgot the term, the number of branches coming from each point. Let's put it like that. This is called Z, coordination, called coordination number. You say that you have coordination number, let's say 3. It means from each point you have 3 bonds. From this point, you also have 3 bonds, and from this, and from this, and from this. This is called beta lattice. The simplest example of a beta lattice is Z equal to, this is just one-dimensional spin chain. From here, you have only 2 bonds. From each point, only 2 bonds. For any beta lattice, we can calculate this exactly. I have a formula. I'm not sure I should write it down, but maybe just to scare you. Well, I almost finished the blackboard. F of p is equal to z minus 2 p gamma p plus z minus 2 gamma z divided by z minus 2. So you can calculate it exactly. For higher dimensional lattices, which are not beta lattices, conventional ones, we do not know how to calculate this fp, but you can say that fp can be approximated the same naive way we were trying to do before. You can try to say that this is smaller than the number of clusters, and number of clusters is growing exponentially, multiply by some factorial, because factorials will be accounting for the histories. So this is your default thing. If you do something like that in higher dimensions, you will have this result. But instead of exponent to the power beta, the correct result will be the following. So this is smaller or equal 1 minus q divided by q0. This is in d larger than 2. And again, q is equal to 2 beta j minus 1. Okay, so you will have critical temperature. There is no way to avoid it because it's a physical thing. You will have a singularity, and this is a not completely naive form of the bound. But what will happen in one dimensions? In one dimensions, we know the explicit result. It's a little bit singular. We can obtain it from this general formula, but it's a little bit singular. I don't want to do it. I just want to calculate it anew. Let's say I have one dimensions, and I have p bonds. And I want to calculate how many ways I can grow these p bonds. I'll say that these p bonds consist of j1 bonds on the left and j2 bonds on the right. Okay? How many ways I can grow p bonds if I have j1 on the left and j2 to the right? In one dimension, the growth is very simple. At each step, you either grow your cluster to the left or you grow your cluster to the right. So the proper history is a consequence of history steps to the left and to the right. You have j1 possibilities to go to the left and j2 possibilities to go to the right. How many ways you can arrange j1 left and j2 rights? It's a number of strings consisting of j1 zeros and j1 and j2 ones in any order. And therefore, I need an eraser. And therefore, a much better way to do calculation in one dimensions is the following. Phi of p is literally equal to j1, j2 factorial divided by j1 factorial, j2 factorial. This formula is a binomial coefficient. This is simply the number of ways to order j1 left and j2 right in a line, right? So this is just trivial combinatorics. Let's take this formula and plug it here, okay? So what will I have? I will have a sum from j1 from 0 to infinity, sum from j2 from 0 to infinity, q j1 multiplied by q j2, j1 factorial, j2 factorial. This is simply e to the q, right? Now, if I have a spin chain which is half infinite, which only has one half and another is infinite, and if I put an operator on the boundary, instead of e to 2q, I will only have e to the q. If I put the operator close to the boundary, I will have eq and then some polynomial piece, okay? All right, so I derive this bound. How to approach this bound? To approach this bound, let me quickly do it in one dimensions. In one dimension, the calculation is very simple. I need to sum from j1, which counts things. So let's say this is my operator A, this is my operator B, and the distance between them is L. I need to consider clusters which stretch to the left to the j1 and stretch to the right on j2, but j2 has to touch B or go beyond B. Otherwise, this commutator will be 0. So the calculation is very simple. I sum over J1 from 0 to infinity. I sum over J2 from L to infinity. And then I have Q, J1, Q, J2, J1 factorial, J2 factorial. I have e to the Q. And here I have Q, L, L factorial plus Q, L plus 1 factorial, and so on and so forth. If L is incredibly large, only this term is dominant. And when this term becomes a order 1, it means that I actually have a second exponent. It means that my operator has spread up to B. Okay, so that gives you the Lib-Robinson in 1 dimensions, which I already announced before. Okay, so I have 4 minutes, 4 minutes. Let me recap. I introduced some new way to recount clusters with a focus not on clusters, but on cluster histories. Of course, I cannot estimate each individual commutator by itself, but otherwise I do precise combinatorics on beta lattices, including 1-dimensional lattice, and I obtain the bound. So I have a good reason to believe this is a good bound, because in Euclidean time, all of them come with the same sign, and a finite fraction of those guys act constructively, then I will have something like this. So my expectation that this bound gives you characteristic behavior for non-chaotic systems, for chaotic systems, non-integrable systems, is based on the fact that in non-integrable systems, all of these guys will not be conspiring with each other. So the finite fraction of them will be adding toward the same direction. In the integrable case, these nested commutators might start canceling or rather oscillating with the alternative sign, so you will have something completely different. Now, I don't have time to explain how to get an intuition about integrable case. Well, but maybe I can say something. Let me remove this thing. Now, we only worked with infinity norm, but there is this beast, the autocorrelation function. You can put here any time. This is the same as trace. This is the same as trace A minus I beta 2, A minus I beta 2 dagger divided by trace identity. So this is nothing but Frobenius norm of the guy I minus beta 2 squared. This autocorrelation function is a Frobenius norm of this operator. And it has to be bounded, well, it has to be bounded by my bound, right? So if I do this, I immediately get interesting results, right? This is a Frobenius norm. Sorry, this is a Frobenius norm, and it is bounded by minus I beta 2 infinity norm squared. Infinity is what I was calculating. So by recognizing that the autocorrelation function in Euclidean time is a Frobenius norm, this is a very simple observation, that immediately tells me that in 1 dimensions, the autocorrelation function will be entire function in the whole complex plane. That was known. And it will be analytic around 0 in higher dimensions. In higher dimensions, it will be analytic in a strip. There will be a singularity. The singularity will be sitting exactly at this time where this norm diverges. Okay? So I have a bound on the strip of analyticity of this autocorrelation function. If you have an integrable model, you will not have the singularity. In the integrable model, this function will be analytic, even in higher dimensions, will be analytic everywhere. At least that's the expectation. I don't know if there is a theorem, but that's the expectation. Okay, and since you have that analyticity, you can go back and see that the propagation velocity will be different and so on and so forth. Now, I have only 1 minute. Let me just jump, very, very quickly, jump and say the following. Huh? 1 minute, right? Okay. So let me just jump and say I can use this result of analyticity. I can use the fact that I have this strip of analyticity to relate this bound to what was recently discussed by a group from Berkeley, the growth of Lanczos coefficients in the recursion method. And they were able to connect this growth of Lanczos coefficients to the Lyapunov exponent of out-of-time order correlator. I'm skipping explaining how they did that. Essentially, they did it only for 0 temperature. They claim that's a rigorous result. For finite temperature, they say it's a conjecture. if I'm skipping all of that, but basically using their result, outsourcing all the derivations to them and all responsibility to them, and I'm just feeding my bound on the singularity into their result, I can have a new bound on chaos. This is a conventional Lyapunov exponent of Atok. And then I have the conventional Moldesena-Stanford-Schenker result in the numerator. And in the denominator, I have 4t beta star. What is beta star? Beta star is this point of singularity of the correlator in higher dimensions. It's related to some geometry of lattice divided by 2j. The coupling constant of my model, which homogeneously bounds all local Hamiltonian, some geometry. So B star is a characterization of my model. This is a bound. In reality, it will be some effective thing. But basically, I have a new bound on chaos, which is valid at all temperatures. At very, very, very small temperatures, this term is negligible. So we recover back the Moldesena-Stanford-Schenker bound. At very, very high temperatures, we have constant. And that is a result of the Berkeley paper. They had that. But what we did, we have an extrapolation formula which works for any temperatures. Okay? So this is an improved bound on chaos. My time is over. Thank you very much.
Is there any question?
Very, very interesting results. I mean, just want to still one word about your motivation. I mean, maybe point which might be interesting, but of course in statistical mechanics we are looking at e to the minus beta h, but we would never ever even imagine to estimate any of these norms. And so the question is, I mean,
what is the motivation? Well, there are several parts to it. There is a mathematical physics part, why I needed this norm. Well, okay, let me say the physics motivation. First, physics motivation is that we're interested in understanding what quantum chaos is. And from that point of view, we want to understand which physical quantities distinguish chaos from integrability. We have the out-of-time order correlator, which people believe knows about chaos. It's a complicated thing. It's a 4-point function ordered in a particular way. Here I'm saying that you don't need 4-point function. You need the autocorrelation function, this 2-point function, or maybe just a norm of operator, and that will already tell you whether your model is chaotic or not. Okay? So this is one motivation. It looks like you're not satisfied. You don't believe it. Well, that's even worse than not being satisfied. There is another more technical reason why I'm interested in this object. This object tells me the following. If I have some finite temperature calculation, this is a conventional temperature now, and I have some operators A, B, and so on and so forth. Sometimes I want to know how much order matters. So to understand how much order matters, I need to be able to permute this guy with this guy. To permute this guy with this guy, best way to do it, well, one way to do it is to write something like this, and then to say that this is a time-evolved A. Okay? And why I needed that, because essentially our original motivation was a little bit far away. We wanted to show that second Rayleigh entropy is a well-defined thermodynamic quantity. Second Rayleigh entropy is potentially sensitive to exponentially small variations of your density matrix because of Faness inequalities. So strictly speaking, there is no proof in the literature that second Rayleigh, the density of second Rayleigh entropy or any other higher Rayleigh entropy is a good thermodynamic quantity. It might be that you change your Hamiltonian at one site, and your second Rayleigh entropy is changing completely by order 1. So we tried to show that this is not the case, and we essentially succeeded. This is unpublished work, and as a part of this rigorous proof, which we are working on, we needed to commute things inside the thermal correlator, and for that we needed to understand how much the norm of Euclidean operator will grow. Okay? But then, while working on that, we realized that in integrable models, we can do much better than this naive bound. And then we understood that quantum chaotic systems and integrable systems behave very, very differently in Euclidean time. All right.
So I could be wrong, but in one of the previous talks, even at this conference, it was mentioned that, of course, in one dimension, there is no phase transition in quantum systems. And the name of Araki came up.
Yeah, that's, yeah.
And this, I think, what people call Araki analyticity.
Yes.
Yeah, it's buried in a paper from the 60s.
We rederived Araki analyticity. I'm not sure if our result is as universal, but essentially the analyticity of our result in one dimensions was guaranteed by Araki. So that's,
right. Yeah, but I think the derivation is also the same. I think so.
It cannot be literally the same. It could be.
Okay, no. So it's not.
Because I know the paper by Araki. I don't think I don't think anyone was counting those histories. I believe, maybe I'm wrong, but I believe this way of counting histories particularly is our new way to do it.
Okay, but can I still make one remark? Or because it's, as you said, it's very interesting in 2 dimensions to have a proof that you cannot get a bound like that, right?
It's very easy to understand that you cannot have a bound. Well, it's not, naively you would think this is related to the phase transitions into dimensions, but that's really not the case. You can just look at any model, for example, SYK model, where 2-point function will have divergence in imaginary time. Sometimes you can just calculate this 2-point function and see that it can have divergence. And if it can have divergence, if this object has divergence, this object must have divergence as well. So as soon as you have a result that 2-point function, and this can be related very easily. Actually, let me just quickly say that. Since this is a 2-point function, you can represent it as Fourier integral. You can represent it as a Fourier integral. So the divergence of this guy in Euclidean time is related to the fact that this power spectrum decays exponentially, but not faster than exponentially at infinity. As soon as it decays exponentially, there will be a singularity. In integrable models, it decays faster than exponentially, and therefore there is no singularity.
We'll give the micro, but there is a student of Joel Lebowitz who constructed models in 2 dimensions where exactly the terms in the expansion, there are no cancellations, and then he shows that there is the singularity.
Perfect. That's amazing. I would love to know more.
So just as a clarification, so I should not think that the beta star is related to the beta critical of the Hamiltonian.
No, you should not. You should not. Because they're not. You can have an Eisen model where you have Curie temperature, you have a phase transition, but Eisen model just with only sigma z's is such a simple model that operators will not grow because all terms commute. So in fact, this formula is completely incorrect for 3-dimensional Eisen model. In 3-dimensional Eisen model, this formula will not have a singularity or pole, while this partition function will have non-analyticity. So at first glance, you think that beta star is related to Curie temperature, but it's not the same thing. I do not know. I do not know. I'm not sure. I'm not sure. Well, the result for the integrable models is based on some known results in the integrable models. If you have a desire to generalize a claim that the result is universal, you can do so. I personally think this is a true statement that in integrable models you will not have a singularity. Because you cannot have exponential decay of a power spectrum, but I do not know how well established this result is. I would say this is more like a lore. This is sort of a general expectation. I have no idea. I mean, if it's a two bonds or 3 bonds, you can renormalize those bonds, making the dimension large and maybe have something like that. If it's a power law, I don't know. It's a good question and maybe not very difficult to work out, but I didn't think. Oh, absolutely. No. I think this is a doable thing. It's a good thing. I just never had a chance to work on that. I need to publish this paper first. Hopefully, I will post it next week to archive. Then I might try to answer all of those questions.
Very much.
All right, thank you.